Good morning. In today's class we will complete the choice of chemical propellants. By choice I mean the criterion what we need to follow, how we say this propellant I can choose, because there are so many chemicals. What are the chemicals we use? We will see with respect to solid propellants, we will say with respect to liquid propellants, maybe we will also see any other form of propellants like hybrid, and make a judicious choice, and then we will go into details of the propellant used in a solid propellant rocket, which we call as a solid propellant rocket. We will look at liquid propellant rockets and the other types of rockets. But before I get this, something from the last class which I must clarify. When we consider ramjets, when we consider scramjets, does dissociation play a role? Like for instance, let us make a diagram of the performance of a scramjet or a ramjet on a TS diagram. What do you do in the intake? I isentropically, let us say an ideal condition, I isentropically compress the air from a temperature 1 to 2, isentropic compression. Then what is it I do? I add heat at, let us say, constant pressure, and then what I do is I expand the gases again. Let us say constant pressure heat addition could be like this, the pressure constant pressure lines are like this, then I expand the gases again. Now if I were to do this, if I keep on compressing the gases more and more, what is it? I have a temperature here which is high, I want still further expansion, I go to still further temperature over here, I have still higher compression, I go to still higher temperature over here. In other words, as I go to higher and higher temperature, the air which is getting in will get dissociated and the temperature will be higher, and if the temperature is so high that I cannot add any more heat release, I cannot have any engine operating. But the question is, if I now I say okay, I will still increase my amount of heat addition. Now even though the temperature here is higher, I increase the amount of heat addition to still a higher value. If I increase the heat addition to a very high value, I get intense dissociation and the chemical energy is not really available. Therefore you do get some bounds. Dissociation plays a role in the choice of the upper bound of temperatures in which some of these engines can operate. Let us keep it in mind, dissociation is not very peculiar to rockets itself, but to all other forms of engine, because as per the rule for a Carnot engine I would like to get the high temperature to be as high as possible. That is when I get maximum efficiency. That is, any engine, if my highest temperature is higher, I get a higher efficiency, because the efficiency of a Carnot engine is equal to 1 minus low temperature divided by the high temperature. If I can make the high temperature to be infinity, I get a very high value. But to be able to achieve these temperatures, I cannot do so, because gas begins to dissociate. That means I will be using my chemical very poorly if I have to go to a high value of temperature. Let us keep this in mind. Another point which I also thought I must make is, it is not only the species which are getting dissociated, but when I go to high temperatures I can also get H plus, I can get H minus, I can get the plasma coming over here, and I can write the equation to these plasmas using the equilibrium constant and also find out how much of the atoms get into maybe the different forms of excitation. I think these things we must learn to do, and maybe we should do it in the project which each one of us will be doing on dissociation, right. Having said that, I think let's keep the focus of this class very clear. We want to examine the different choice of chemicals which can be used for solid propellants, liquid propellants, hybrid propellants. What are the things we have done so far? We said, well, I would like to get a high value of heat release, I would like to get a high value of temperature, I would like to get a low value of molecular mass. Well, gamma really did not matter much to me. Well, we just looked at this point, but a chemical must be handleable. That means a chemical must be capable of being stored. it must not be something which absorbs air from the it absorbs moisture from the air, is sort of hygroscopic. It is something which must be stable. It must not happen before I start using the chemical, it begins to do something. Therefore, there are other factors in addition to this which also plays a role and which we will be seeing as we study the different propellants. Well, having started this, let us get into some details. Well, solid propellants, we have already seen the different chemicals. Let us start with the chemical with which we started in solids. We said I could use something like nitrocellulose, which we said is an explosive. And what was the formula for nitrocellulose? We had something like C6H10O5, was it, or is it O10H5? C6H10O5 was cellulose, and what I did to the cellulose is like paper. This could be written as C6H5OH5, and this comes as a chain, you know, like if I have a paper, it is just, we say, a cellulose material, it comes as a material as a chain like this. And what I do is, for nitro, I substitute part of OH by the nitrate radical, that means nitro group, I get C6H5, I am left with sum of OH, namely 5 minus X, and I put instead of OH ONO2 X, and this is what we call as nitrocellulose. We talked of this earlier in the class. We told ourselves, well, this contains both oxygen and carbon, terribly fuel rich, but can still dissociate to form carbon dioxide, maybe CO, maybe other species could come out over here, and this could be used as a propellant. In other words, we could call it as a single base propellant because it is a single explosive which dissociates and does the job. I could have another propellant, the other thing we said is nitroglycerin, and we told nitroglycerin is little better than nitrocellulose because nitrocellulose had a very large and negative value of heat of formation. Nitroglycerin was better that way. And what was nitroglycerin? It was derived from propane, C3H8. What we take propane, we take 3 of propane, 3 of hydrogen out, substituted by OH, namely an alcohol, we call it as C3H5OH3, which we call as propane triol, that is 3 of OH. This is known as commercially as glycerin. What we do is, instead of OH, we substitute it by nitro, that means we have C3H5ONO2 3 times, and this is what is known as nitroglycerin. Again, in the classes we found this is slightly oxidizer rich, but it contains O, C and H, it can be used by itself. Well, this is also a single base propellant. We call it as a single explosive propellant or a single base propellant. Just like nitrocellulose, which was fuel rich, which could be used, this is slightly oxidizer rich and it could be used, but these are very seldom used by themselves. But what is done is, you mix nitrocellulose and nitroglycerin, that means you have 2 constituents, and this is what is known as a double base propellant. Therefore, the first solid propellant what we study would be, let us put it down, will be a double base propellant, which is still used widely. It consists of nitrocellulose and nitroglycerin. Nitrocellulose is fuel rich, nitroglycerin is slightly oxidizer rich, and you get much better performance than if these were used individually. How do we make it? Well, we take nitrocellulose, we put nitroglycerin in it, make it as a colloidal solution, add some more additives to it. What are additives? You know, whenever we make a propellant, it is just mixing the thing and forming some hard material because we want it as a solid. And what do we add? We add some plasticizer such that it becomes more plastic. We add something which will make it flow because I would like the two to mix together. we add some plasticizer, we do this a small part of it, we make it into a liquid, we cure it, make it as a solid block, and this solid block what we call as a propellant grain or a propellant block. Let me put some names of the plasticizers which are added, just to make sure we are in the field. We add plasticizer. I will come back to this plasticizer a little bit. Plasticizers used are something like triacetine. See, I do not like these names because some of us do not even know what it means, and there is not much point in knowing, or something like diethyl phthalate. What do we mean by a plasticizer? Something which makes it a little more plastic, that means it makes it a little less sensitive to impact. Something solid, when it is hit, it gets a spark, the plastic sort of absorbs this, but at the same time it gives some more consistency to it, and therefore the first propellant we say consists of nitrocellulose and nitroglycerin with a small amount of plasticizer such that I can make a solid block. This becomes nitrocellulose and nitroglycerin form a single molecule, or it is mixed so perfectly that it is homogeneous. And the double base propellants are also called homogeneous propellants. The mixture is essentially something like a colloid. Colloid means you have suspension in liquid, and therefore this is also known as colloidal propellants. The trade name for a double base propellants is cordite. We have a factory at Arvancado in Nilgiris which specifically manufactures cordite propellant for use in defense and other purposes. Therefore, we say that the first one is we learnt about nitroglycerin, nitrocellulose together. Individually these are single base propellants, together they form something known as a double base propellant because you have two bases, and we also add some amount trace quantities of plasticizer and some more additives to make sure that the final product which is formed as a block of solid fuel is something which is workable. I would like to machine it, I would like to do something, and that is what we will see when we study solid propellant rockets. Because if I want to make something, I want a block, I need to have a fixed dimension. I would like to have a rocket in which this goes and fits in, I have to machine it, I have to make it length, so that to make it workable I need to add certain things to it, I cure it and form it as a solid. Therefore, the first propellant we deal with is double base propellant, and these are essentially nitrocellulose and nitroglycerin. Let us go to the next type. There are only 4 types, and out of which the second one what I am going to tell you now is something which is very widely used, and that unlike a homogeneous propellant, what is that? This is homogeneous, that means everywhere it is exactly same. If I cut it, I cannot find out the different striations or anything. The second is what we call as heterogeneous. Propellant. This is also known as composite. As distinct from these double base propellants which are uniform, which are something like a single molecule or uniform throughout, composites are very heterogeneous. What happens is you add oxidizer in a solid form, you add maybe aluminum again as a fuel, perhaps not always aluminum, and then you glue it together using some particular fuel. What do you mean? All of us have talked in terms of this black powder when we talked of the course in explosions. What was black powder? We had KNO3 which was ground, we had carbon which was ground, we had sulfur which is ground. We said we mix the 3, put gum over it and make it as a paste and use it as something which is an explosive for fireworks. So also you take a composite which consists of an oxidizer, maybe some fuel, and maybe the thing which is bonding together could act as a fuel. Therefore, a composite propellant will consist of an oxidizer which is something like a solid crystal, solid ground crystal, a fuel which could be aluminum. The same fuel could also be the binder which binds the solid crystals and aluminum together, or it could be something like a hydrocarbon. Therefore, as distinct from homogeneous propellants, a composite propellant consists of an oxidizer, a fuel, and this fuel could also be the thing which is gluing things together. Let us take some examples and this will become further clear to all of us. Let us see what are the type of oxidizers we could use in a composite propellant. One of the oxidizers which is very widely used is ammonium perchlorate. We call it as AP, which is NH4 ClO4. Mind you, it consists of hydrogen, but amount of oxygen it contains is so high that it is still an oxidizer. Maybe NH4 ClO4, maybe this is why very widely used. It dissociates easily, it is not hygroscopic, it can be easily stored, can be made as small particles and all that without any problem, and that is why ammonium perchlorate is the most preferred choice of oxidizer for solid propellants. We also have other things. We have still more energetic like Hydrazine Ium Perchlorate. Let me get the chemical formula of it correct. Yes, it should contain some hydrazine, that means it should be N2 H5 ClO4, and another one which is Hydrazine Ium nitroformate, and the formula for this will again be Hydrazine Ium N2H5 into CNO2 3 times. These two things are still something which are being investigated upon, but the only oxidizer which is widely used is still AP as it is. We have things like coated AP instead of having the raw AP, such that it is more easily processable. I will come back to that point a little later. Therefore, we say, well, we could have choice of different types of oxidizers, but the oxidizer which is used, we could use maybe NH4NO3, it also contains, but it is hygroscopic, not much energy. We could in fact use KNO3, but again the K has a larger value of atomic mass, and therefore it is not a preferred fuel, and therefore whatever be the oxidizer for a composite propellant, ultimately what is being used today is only ammonium perchlorate. This is all about oxidizers for the composite propellant. Let us take a look at the fuels which are possible, and then we will put the things together and see what is involved in a composite propellant. When we say fuel, I also told fuel could be a hydrocarbon fuel. Let us see what are the different types of hydrocarbons and how we use what hydrocarbon. Let us start the hydrocarbon chain. We know hydrocarbons consists of aliphatic compounds, and I think little bit of organic chemistry is always useful. Aromatic hydrocarbons. Aromatic are those which have a strong smell, and why does the smell come? Because you have the benzene molecule in it, whereas aliphatic compounds are either straight or polychain compounds. This could be either saturated, we call it as alkanes. What do you mean by saturated? All straight chain compounds. Carbon chains are all straight over here. The second we said is alkenes, one double bond. 1 double bond, 2 and 1, 1 double bond, or the third one could be alkadines which have 2 double bonds, maybe something like this, 2 double bonds, or rather I put a single bond here, I put a double bond here. C4, yeah. We could have single chain, we could have 1 double bond, all single bonds, we could have 1 double bond which we call as alkenes, we could have 2 double bonds which we call alkadines, we could also have 1 triple bond like acetylene, C2H4. The triple bond is highly unstable, acetylene is an explosive, therefore we cannot use such compounds. We are trying to find out how we choose a propellant, and that is why I am going through this. If we have alkanes, well, the example is methane, CH4, CH4, maybe I have C2H6 ethane, C3H8 is propane. Mind you, all these are all gases, I cannot use the gases anyway, but there is a tendency today to liquefy the gases like liquid methane, liquid propane and use it. I will come back at the end of this class. Therefore, we say these are gases not that useful. How about butane? Butane is also a gas, C4H8. Let us take the butane form of alkanes, alkenes and alkadine. Let us put it together. We said butane formula is C4H10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Formula is C4H10. This is butane. If I were to talk in terms of butene, mind you, butane is a gas. Let us go to the next form. Well, I have double bond, butene, and of course, I will have all the chains as it is. 1, 2, 3, 4, 5, 6, 7, 8, C4H8. And if I now have butadiene with 2 double bond, well, I have 2 double bond and the formula will be C4H6, because I proportionally I have to decrease 2 of the hydrogen. Now, amongst these all choice of these aliphatic compounds what we are talking of between alkanes, alkenes and alkadines, this structure is something which you do not lose so much of heat of formation. See, another thing which I forgot to tell you was we found that the heat of formation of methane was small negative value, the heat of formation kept increasing, and therefore very complex substances were not desirable. But alkadine we do not use much, therefore what we use is something like a polybutadiene. What is polybutadiene? I take a butadiene molecule and I keep on making it into a chain, and this is something which is very widely used as a fuel. But polybutadiene is just carbon with maybe the hydrogen over here is what I get, and to be able to form a good fuel out of polybutadiene, what I do now, I come to the actual fuels which we can use or the binding agent. I want to make it into a good polymer, something which has a long chain which can keep the oxidizer particles in it. Therefore, I take this polybutadiene whose structure I have just given. Maybe this is something which is a chain, a chain is something which is elastic, it will keep on pulling. I need to make it a little strong such that it can hold things together. Therefore, I add something like acrylic acid and or else acrylic acid and maybe acrylonitrile. What is acrylic acid? I have CH, CH2, giving carboxyl acid COH, this is the maybe X times this is what is acrylic acid. Similarly, acrylonitrile is CH2 maybe Y of CN acrylonitrile. And what is it I do? I have this chain of polybutadiene C, 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 this is a polybutadiene molecule M. At the end of the chain I put an acrylic acid CH, CH2, COOH, maybe a few of them, then I put something like CH, CH2 and I have CN over here. And what does this do? It gives something like a chain. It is not only a chain, but it is able to go in the lateral direction. It gives some rigidity, and therefore I have something which is known as polybutadiene acrylic acid acrylonitrile. That means I put the acrylonitrile and acrylic acid together. I call this as PBAN, polybutadiene acrylic acid acrylonitrile, and this is one of the fuels which are used for solid propellants. You all would have read somewhere, yes, PBAN is used. PBAN is used in the space shuttle in huge motors. Why it is used? Hey, it is possible to make it as a binder, and it is possible to have the rubber part of it to have some more hardness and strength, and that is how you use the polybutadiene. Therefore, we say, well, the first fuel which I can think in terms of using for a solid propellant is polybutadiene acrylic acid acrylonitrile, which I call as PBAN. Okay. See, PBAN is something which is sometimes hard, I have this cross linking by all these things, it tends to be hard. And second is I have lot of carbon here, carbon has a heavier mass, and therefore is it possible to somehow get rid of nitrogen here, just substitute it by the carboxylic acid, namely the acid part of it. That means I terminate the polybutadiene with a carboxylic acid type of situation, and this is known as CTPB. That means carboxy terminated polybutadiene. That is the second fuel. There are not many, just some 2-3 of them. All what we have done is we remove the acrylonitrile part of it, keep the carboxyl acid here, and we stop the chain here. Maybe it gives little better properties and little more energy than a PBAN propellant. But the choice for major booster today is still PBAN. We see whether some improvements are possible. The question is, why not have a polybutadiene in which I do not terminate it with anything, but I just put something like OH here, I put OH here. In other words, I have hydroxy radicals which are used at the ends of the chain of this, and now I have the another of polybutadiene C, 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 again maybe N, again something like OH. I keep on terminating. At the end of the chain I put hydroxy radical, I call it as 3 hydroxy terminated polybutadiene. The advantage of using OH is hydrogen is available, it is much stronger and it is more energetic, and therefore the most popular propellant today or most popular fuel for propellant is HTPB. The reason being it is little more energetic, but for boosters, for large boosters, I still find PBAN continuing to be used. Well, the most popular fuels are PBAN and HTPB today, and I think we must keep the reasons very clear. Yes, this is more energetic because it contains H compared to C and N or C and are not there anymore, but basically we have the polybutadiene chain which is terminating in these type of chains over here. These are the type of fuels what we use. In fact, HTPB is very widely used in the tire industry, and it is also something like rubbery material which is used in the tire industry, but for propellants it is something very much useful. There are 1 or 2 exotic chemicals which are being talked of as fuels. I think we should get some names of them. we talked in terms of some fuel which is being talked of nowadays. We call it as GAP, which is known as glycidyl azide polymer, and this has a formula something like CHNO. In different proportions it is being tried, something like C5, H9, then NO and stuff like that, but I will not get into these molecular formula, but we must keep in mind that GAP contains little more hydrogen than even HTPB, and some research work is going on using GAP as propellant. It is still not used, but there is some work going on, and I think as people who are doing postgraduate, we must know what is the current line of research, and the current line of research is to increase the energy content. How do you increase the energy content? Have more hydrogen like a hydroxy terminated polybutadiene. Therefore, what is it we said? Well, oxidizers for composite propellant could be AP, the fuels could be something like this. Well, we could add aluminium powder. What is the advantage of aluminium powder? It could form Al2O3 in the exhaust products. We said Al2O3 has a very large negative value of heat of formation, and I could get the energy from aluminium. Therefore, a composite propellant basically consists of these three, maybe an aluminium powder which we said is a fuel. It could consist of a binder, maybe let us take HTPB as a fuel. It is also used for binding aluminium and AP crystals. This is what is a composite propellant. If it is non-aluminium, it could still consist of HTPB, or it could consist of maybe CTPB or PBAN plus ammonium perchlorate. These are what are called as composite. Composite because ammonium perchlorate comes as crystals, small spheres or particles, and this you bond together using the binder over here. This is a non-AP, non-aluminium propellant. If I still put aluminium powder in it, well, I get this particular composite propellant. These are the composite propellants. Therefore, whenever I talk of composite propellants, I have in mind something like a polymer, I have in mind something like ammonium perchlorate, and maybe some metals. It need not always have a metal. If you want more energy, I put a metal, and in defense very often if I put metal and I see a rocket going up, I get lot of high temperature exhaust, and that is something which is seeable, a radar can see it, and therefore they try to use either a double base or some other form of propellants which does not have that signature. We will take a look at some of their requirements. In the past, instead of PBAN or CTPB, see, we must be able to distinguish how these things come. Maybe HTPB, they made use of polyvinyl chloride PVC, and what is PVC? It consists of CH, CH2 with Cl in a large chain, but these are all very low energy. Nowadays it is just not used. People tried polysulfide, people tried foam which is polyurethane, let us write it out, polyurethane, which is just like the foam what you use in your mattress. These have been tried, but these are all very low energy fuels, and therefore it is not used anymore, and what is used is essentially HTPB, PBAN, and to a certain extent CTPB which is used, and these are the different types of composite propellants. Therefore, we tell ourselves, well, the second form of propellant is a composite propellant. It consists of a composite of oxidizer particles, maybe metal particles like aluminium, and a binder or a polymer which connects all of them together. Therefore, we talked in terms of double base propellants. Second, we talk in terms of but there is something in this, See, the problem is I have oxidizer, let us say I have spherical oxidizer particles, I have AP like this, like this, like this. If I have a single size of AP, the amount of AP I can put together will be small, whereas if I can have double sizes, let us say I have AP size of let us say 300 microns, then if I were to fill with AP and I have binder which binds all these things together, it is going to bind it like this. Here I have polymer, here I have polymer. You know what happens is the amount of AP which I can put in the propellant is small. We call it as AP, a solid, which is a solid loading in a propellant. Now instead of having 300 micron size, if I make AP of two sizes, maybe I make 300 micron size and another one I put 3 micron size, or let us say 30 micron size, 3 is very small, then what is happening is the small particles can be put over here. That means I can increase my loading of AP in the propellant. Therefore, in almost all the propellants, composite propellants we use today, we just do not use a single size of AP, but we use a bimodal size typically between 300 and 30 micron. Why it is used? I want to increase the amount of AP as much as possible, and when we use aluminum, aluminum is even smaller size, typically around 5 micron size of aluminum. And why aluminum? Aluminum is again a solid, I can improve the loading of solid, and therefore I can have a dense propellant as it were. And this is all about composite propellants. Well, the other two propellants in solids are derived from these two. We say composite modified double base. We have already seen double base propellant is nitrocellulose and nitroglycerin, right? But supposing I want to increase its energetics, increase the reaction and energy release, that is add oxidizer ammonium perchlorate used in composite to double base propellants and make it more oxidizer rich. I could also add explosive to enhance the energy, and the explosive I add is something like an explosive known as HMX. What is an explosive? It consists of fuel and oxidizer together. This HMX consists of something like cyclo tetra methylene tetra nitramine. You know, HMX stands for Her Majesty's explosive because it came from UK, and the chain is maybe C, you have N here, you have C here, you have N here, you have C at the center, N here, you have C here, you have N over here, and then you have the methylene radical, maybe CH3, and you have NNO2. This is just an explosive, and I do not think we should spend much time on it. All what you do is you add a HMX to small quantity of this, it becomes a composite of a double base and this particular HMX explosive, and this is known as composite modified double base propellant. It is used widely in the defense because they would like to have their missiles which are more energetic than double base propellant, or they would like to have properties of the propellant which can be readily formulated. It can withstand some amount of strength, because a propellant must also have some strength because it is bonded to the case and it must not get detached from the case, or it must not develop cracks and all that, and that is why we find composite modified double base propellant, we will call it as CMDB. Therefore, the third propellant we say is a mixture of a double base and an explosive, and the last type of solid propellant is what we call as nitramine propellant. You know, all these propellants have distinct characteristics. You know, why CMDB? It will have a burn rate with pressure having something else. We will consider this when we study the solid propellant. We are just trying to take a look at what are the chemicals which constitute the different propellants and what are the different solid propellants what are available. When I say nitramine propellant, we have a binder like HTPB, which is a polymer. into the polymer, let us say HTPB, you add something like HMX, which is an explosive, or a slightly less energetic explosive is something which we call as cyclo-trimethylene trinitramine. And what is it different in structure? It is tri now, therefore you have C, N, C, N, C, N going to C, you have CH3, 3 of them, NNO2, therefore you put an explosive into the HTPB binder, and that what you get is something which we call as a nitramine propellant. What is the advantage? See, HMX is fuel rich, HTPB is fuel rich, therefore what happens, you do not get high temperature, but you get it is able to generate gas at low temperature and still propel your vehicle. Therefore any enemy cannot see that a vehicle is going up, because he uses a radar to see the temperature of the plume. Therefore each one has its own advantages, plus the burning rate will change. I will look at it when I consider solid propellant rockets. In addition to adding HMX, this particular thing is what is known as RDX, research and development explosive, which is cyclo-trimethylene nitramine. You add almost 80 to 85% of these explosives, one of these explosives, to HTPB, and that is what is known as a nitramine propellant. Of late I find AP is also being added to this, and this is also called as AP plus HMX or RDX and HTPB is also what constitutes the nitramine propellant. Actually the research which goes on in the area of propellants is, maybe you have something known as glycidyl azide polymer, and these things have more hydrogen, and into something like a fuel like GAP you add HMX RDX, and it could not therefore be only HTPB, but an glycidyl polymer which could also be used instead of a fuel. I think I will not get into some of these things. Glycidyl is again something like a CHNO system. We will not get into too much of this, because our main concentration would be the composites, maybe the double base propellants, how they burn and how they are developed, and therefore we say the solid propellants essentially consists of double base, composite modified double base, and nitramine propellants. We will look at their characteristics when we study the solid propellant rockets. Having said that, let us go to liquid propellants. They are extremely simple, much simpler than what we talk in terms of solid chemicals, and they are classified in a slightly different way. We do not classify them into 4 such categories. We just say liquid propellants are categorized into 3 categories. We call it as low energy propellants, medium energy propellants, and we call it as high energy propellants. Maybe by now you all can tell me which will be high energy and low energy. Energy is a misnomer in rocketry, because it is not only energy which is important, but a low molecular mass is also important. Therefore we told ourselves hydrogen oxygen has a low molecular mass, even though the energy may not be high, and therefore when we say high energy propellants, we always mean high ISP propellants, medium ISP propellants, and low ISP propellants. Propellants which have sea level ISP less than 3000 Newton second by kilogram are known as low energy propellants, which are between 3000 to 4000 are known as medium energy propellants, and those in excess of 4000 Newton second by kilogram are known as high energy propellants. We immediately tell ourselves, well, hydrogen oxygen is by far the best, and therefore the high energy propellants are hydrogen and oxygen. Perhaps hydrogen and fluorine is also good. Yes, it is even more energetic, but fluorine is highly reactive and therefore it was tried in one mission and dropped. But hydrogen and oxygen cannot be used as room temperature gases, it has to be liquefied, and they are all very low temperature, hydrogen at 20 Kelvin, oxygen at 80 Kelvin. Being low temperature, we call these propellants, high energy propellants, as cryogenic, because it has to be kept under refrigerated conditions, call it as cryogenic propellants. Therefore, if I want to make a missile, I cannot use a cryogenic propellant because a missile must be ready for launch any time. We cannot wait for a war, an enemy can strike at any time. Therefore, it is not possible. Therefore, these cryogenic propellants are normally used for launch vehicles, which you can fill as you want, you can do what you want, you have all the time in the world. But if you want to have something which can go fast, maybe let us take a look at some of the low energy propellants and then come back to the medium energy. What are low energy? We said those which have specific impulses less than 3000. Let us put a few of them together. Well, you know, all of us have read of V2 rocket, which was the first rocket ever made, and it was by the Germans in around 1945 during the Second World War. It used liquid oxygen and alcohol. Alcohol is something like maybe some ethyl alcohol, and ethane is C2H4, C2H6, maybe you remove some of the H and put OH, you have ethyl alcohol, some alcohol, and this was done, but it is very poor performing, very low in specific impulse. But liquid oxygen is something which is a cryogenic liquid. Alcohol is liquid at room temperature. Therefore, you have a cryogenic with a room temperature fuel, and therefore, this combination will be a semi, it is not totally cryogenic, but a semi cryogenic propellant, right. Alcohol has poor properties. Why does it have poor properties? It contains oxygen also, because you have OH. That means it is not a good fuel. Why not use a better fuel like hydrocarbon? Why not use kerosene? Kerosene has a molecular formula something like C12H26 linear chain, no oxygen, it is a much better fuel, and therefore, the present trend is to use semi cryogenics consisting of liquid oxygen and kerosene together. But kerosene as it is, you know, it has something like it can evaporate quite fast, it is little volatile. You would like to make it suitable for a rocket, and the kerosene, which is slightly modified by additives, is what is known as a rocket propellant. Therefore, kerosene has been extensively used in rockets. It is also known as rocket propellant. It is a little different from the pure kerosene in that I have to put something more. What are the things? Flash point of kerosene is around 38 degrees, but you would like to increase it to something like 55 degrees. Therefore, you put some more additives in it and you increase the flash point, you make sure it does not gel or it does not form sediments and all that, and that is known as a rocket propellant. Kerosene is also called as rocket propellant, and it is used with liquid oxygen, and the values of specific impulse are not very high, of the order of 3000 Newton second per kilogram. So, and therefore, it is one of the low energy propellants. It no longer alcohol is used, but we use liquid oxygen with kerosene with the rocket propellant. But unfortunately, there are some problems with kerosene. See, kerosene is not a pure chemical. You know, I go and take petroleum from some well. Some petroleum might contain some more naphthalene, some may contain more paraffin, and depending on that the thing changes, and therefore, people have been trying to get kerosene to be synthesized, to make kerosene in the lab, and the Russians have done it. It is known as syntin. But syntin is costly, it is made from carbon and hydrogen at high pressure in the lab. It is not very widely used, but it is used by the Russians. But what we use is, yes, we should have some control on it, and we say rocket propellant is something like kerosene, almost kerosene, but with some additives added to it. You know, the work which goes on in these fuels is, we tell ourselves, well, kerosene might be like this. If I can strain the molecule, if I can make C like this and strain the molecule, I can put some more energy into it. That means I change the bond characteristics. I can make kerosene to be more stronger or to be even more energetic, and work is going on how to put energy through the bonds and all that. We will not consider that, but we will suffice to say that one of the liquid propellants used is maybe liquid oxygen and kerosene. Maybe there are a few more, I will go through it in the next class, but what I did in today's class is we looked at solid propellants, we classified them into 4 categories. We started with liquid propellants, we saw the high performance propellants being liquid oxygen and liquid hydrogen, and then we were just starting with low energy propellants, and maybe we continue with this in the next class, right. Well, thank you then, I think that's about it.